everyone, this is Lahapi from Sri Venkateshwara College of Engineering. I am studying in 4th SEM and today's topic is about equivalence relation and partition. This presentation explores the critical concepts of equivalence relations and partitions. We uncover their definitions, properties and how they iteratively to shape mathematical reasoning. The defining relation is building blocks for understanding. Relation basic is about a relation connects elements from one or more sets. Set elements. Elements are paired in specific ways defining relations. There are types of relations. One is reflexive and another is symmetric and third one is transitive. What makes a relation equivalent? The three key properties are reflexive property, every element relates to itself. Symmetric property, if an element are related to B and then related to A. Transitive property is about if A related to B and B related to C, then A relates to C. Equivalence classes grouping elements based on similarity. A equivalence class contains all elements equivalent to each other. In simple terms, if two elements are related in a certain way, they belong to the same equivalence class. The equivalence relation must satisfy A similar to A and symmetric and transitive. Partition rule is about each classes form a part of a partition of the original set. Partitioning means dividing a set into non-overlapping, non-empty subsets such as that every element belongs to exactly one subset. In the context of equivalence classes, the set is partitioned into disjoint equivalence classes. Each class contains all elements equivalent to each other. Together, these classes cover the entire set. The example is, we can take that let A is equals to 1 to 5 and A belongs to 1 to 5 where A is equals to 0, 1, 2, 3, 4, 5. Define relation A is to BA and similar to B is to B. If A is equals to B mod 3A, equivalent B mod 3A is equals to B mod 3. Then the equivalence classes are 0, 1, 2 which gives 0, 3 that is 0, 1, 4, 1, 2, 5, 2. These classes partition the set AAA based on the equivalence relation. Partitioning sets, dividing and conquering mathematical space. Step 1 is about divide set into non-overlapping subset and ensure a union covers entire set. No subset shares elements. Where the fundamental theorem behind equivalence relation and partitions are two sides of a coin. From equivalence to partition, equivalence relation induce partitions of the set. From partition to equivalence, each partition defines a unique equivalence relation. Mutual dependence is about they create a bijection preserving structure. Well, this theorem states that there is one-to-one correspondence between equivalence relation and partition. Every equivalence relation on a set defines a partition of the set, and every partition of a set defines an equivalence relation. From equivalence relation, if you define an equivalence relation similar to on a set A, it groups elements that are equivalent into disjoint sets. These equivalence classes for M a partition A, no two classes overlap and every element belongs to exactly one class. For example, from partition equivalence relation, if a set A is a partition subset of A to AN, where A bar 1, A to the power 2 and A to the power n, you can define a relation similar such that A similar to B that similar to A, B, A is equals to B if and only if A and B belongs to the same set. This relation will satisfy reflective, symmetric, transitive. Therefore, it is an equivalence relation. Examples in action about equivalence relation in different contexts. Modular arithmetic. Numbers equivalent mod n creates classes. Shape congruence by transformation for m relation. Elements grouped by similarities in data science. Application of equivalence relations solve real-world problems. Computer science. Optimizing database and compiler design. Social science is about classifying social groups and behaviors. When it comes about mathematics, simplifying complex structures for analysis. Well, data recording grouping. What may be the problem is, in database, we often have records representing the same entity. What it can be the solution for this is define an equivalence relation like has the same email address to the. This helps with data cleaning and deduplication. Student classification. Group students based on grades, age or performance. Use an equivalence relation like has the same group to partition students into classes. Useful for academic grouping, analyzing and classroom management. Network routing like IP subnetting. While grouping IP address in a network is, IPs in the same subnet are considered equivalent. This helps with network configuration and routing rules. Access control system. What it may be a problem is accessing users the same access rights. Has the same role is an equivalence relation. Role-based access controls systems group users by permissions equivalence. Common pitfalls. Avoiding the mistakes when working with equivalence relation. Ignoring transitivity leads to incorrect equivalence classification. Overlapping partitions. Partition must be disjoint without common elements. Mistaking relations versus functions. Not all relations are functions. Clarity is crucial. While common pitfall in equivalence relation are not verifying all three properties, as an equivalence relation must be reflexive where A is equals to A into A and similar to A into A is equals to A. But symmetric if A is equals to B into A, similarly BA is equals to B. Then E is equals to AB similar to AB is equals to A. Transitive is if A is equals to B similar to BA is equals to B and B is equals to CB similar to CB is equals to C, then A is equals to CA and similar to CA is equals to C. Mistakes is about assuming a relation is equivalent without checking all properties. Confusing similarity with equivalence. Not all types of closeness or similarity are equivalence relations. Example, leaves in the same city may fail transitive in dynamic data. Overlapping equivalence classes. Equivalence classes should be disjoint. Every element belongs to exactly one class. Mistakes are about putting the same input into multiple classes during partitioning. Poor test class defining definitions in software testing when using equivalence class partitioning. Some define classes too broadly or ignoring invalid classes. Others pick non-representative values that don't catch edge cases. Example is about choosing 0 for a class 1 to 100 input range, which is invalid. Neglecting boundary conditions. ECP works best when combined with boundary value analysis. Ignoring edge value like 0, 1 or max input will cause a problem. Incorrect assumption about transitivity. Just because A is equals to B and similar to B, A is equals to B and B is equals to CB similar to CB is equals to C doesn't automatically mean transitively holds unless proven. Common in logic or human-defined relation. A conclusion about equivalence relation as a powerful tool. Equivalence relation and partition simplify and structure complexity. They unlock powerful abstraction in math and beyond. Mastering these concepts enable clearly reasoning and problem solving across disciplines.